Cool. Alrighty. So 5 o'clock. So let's get going. At least 5 o'clock UK time. So whilst people are kind of joining the session, so I'll probably just do the usual preamble about who we are and what we do. So I'm Richard. So thanks everybody for joining. We have Jonathan on the line as a backup presenter in case this all goes horribly wrong. So usual reminder that the session is recorded, and yeah, as people drift in, we'll start the preamble. So if my mouse starts working properly. Okay, cool. So we're a team in Arm, currently 3 people who look after the browser's performance and feature sets on Arm platforms. We have 3 main areas of focus at the moment, which is speed, so helping Hans and Chewy do their to-do list more quickly, control flow integrity, which is one of the topics that we'll talk about, as well as memory safety as well. So that's a kind of our 3 primary activities at the moment. Like I said, we're currently 3 people. So we have Jonathan, who is our libjpeg turbo owner and all-round SIMD expert. We have Andre, who's been doing a lot of work to support our 3 key Armv9 technologies, PAC, BTI, and MT. So he's been doing a lot of the low-level work to get the code base ready to support PAC and BTI. And then you have me, who's basically doing everything else. Unfortunately, since the last BlinkOn, we have lost our long-time Chromium.org contributor and zlib owner, Adenison. So 5 years ago, when Adenison started working on zlib, it was kind of stale. It was just a straight C code. It had not really changed very much in the previous few years. Since then, he's added lots of high-performance SIMD neonized encode and decode paths. And today, Chromium zlib is one of the best optimized zlib forks out there. And his work has been widely cross-ported to all of the other zlib derivatives floating around out there. And Chromium zlib is now the basis for various other Google products, including Android. Most recently, he helped us sync against the upstream zlib 2.12, which was something like 15 CLs and a lot of work associated with syncing against that. So on behalf of the team, I would just like to take a second to acknowledge his many accomplishments on zlib over the last 5 years, as well as to other areas of the browser, and wish him well for whatever he's going to do next. We're also soon to be opening hiring for this team. So if any of the topics we cover in this presentation are interesting, do get in touch. My email's on there. Cool. So when we talk about Armv9, we're talking mostly about these kind of 4 technologies. So we version the Arm architecture. Armv9 is the latest version of the Arm architecture. It contains lots of new features over the previous kind of major baseline Armv8. We're mostly going to focus on these 3 highlighted areas. SV2 is our new shiny vector extension. It's very interesting. We don't really have time to go into it in this presentation, and we have lots of very complicated technical problems to solve before we can use it. But hopefully we'll be able to share more about it at the next BlinkOn. So onto our major focus area first, which is MTE. MTE is our name for the memory tagging extension. And the memory tagging extension is a tool to help us find and fix memory safety problems earlier in the development cycle. So the way it works is that essentially, although we are a 64-bit architecture, we don't necessarily use all the 64 bits all the time. So in these unused bits in the pointer, we can use them to store other stuff. And the memory tagging extension essentially allows us to store up to 16 different tags in the top of every pointer, and it then kind of shadows that tag into an area of protected memory that ordinary code can't access. And this means that we can basically verify when we dereference a pointer or write to a pointer that the tag that we think that memory area should be is actually what it is. So this means that we can detect things like use after freeze and out of bounds reads and writes. The way we've implemented in Chromium is that we deterministically mitigate use after free, and we probabilistically mitigate out of bounds reads and writes. So if we go off the end of the pointer into the next allocation slot, we can detect that. And similarly, if the slot has been freed and we access that, then we detect it. And it kind of builds on top of Miracle PTR. So there was lots of interesting discussions last year about how we could use it. I think that discussion is probably still ongoing, at least for the next year. So since the last BlinkOn, we have some interesting updates in MCE in that we actually have some development boards available that we can try out MCE on. MCE will kind of remain a developer-only debugging option for at least this year. We will support it in the meantime until it's more widely enabled on end-user devices. We have some interesting things that we're thinking about using MCE's synchronous mode for security-critical components. So security synchronous mode gives us the most security properties out of any of the MCE modes. There's also asynchronous mode, which is much faster but less precise for debugging. We're also implementing various debug and crash reporting enhancements to make MCE faults more actionable, and that requires a little bit of work on the allocator shim and other things, and Andre's handling that at the moment. We anticipate that this year the use cases will mostly be for quality assurance and validation. We think it's particularly interesting for fuzzing things like image and video codecs, areas that ASAN doesn't really handle very well. So particularly anything with a lot of assembly will be a focus for us with MCE because it's kind of validated at the hardware level. So hopefully more to share soon on MCE. Next up, control flow integrity. So control flow integrity is kind of making sure that the code that you write is actually the code that gets executed. So we have two major control flow integrity technologies in Armv9. The first one is pointer authentication. So pointer authentication essentially allows us to cryptographically sign the link register and insert these pointer authentication bits onto the top. The idea is that then when we later return from this function, we can authenticate those bits. And essentially, we can make sure that the link register that we're returning to is the one that we expect to return to. We've made good progress on pointer authentication, and it's now completely enabled in M102. So for all C++ and JavaScript code, we now have pointer authentication enabled in M102. However, it only is kind of half of the control flow solution. So it protects the reverse edge, but it does not protect the forward edge. So that's what we're doing next. So to protect the forward edge, we have another technology called branch target identification. So this helps us to prevent reaching signing gadgets. So for example, if we take this kind of innocuous switch heavy function that compiles to something like that, I have this on the right. Let's say we have like a small out of bounds write, which allows us to skip the first couple of instructions, this range check up here that decides whether we're reaching something valid within the switch statement. Well, now we've essentially taken this fairly innocuous function and we've turned it into a signing gadget. So if we land on this pack here SP instruction, we can now basically just sign our link register and return to kind of wherever we want. We can potentially kind of read beyond the memory pool over here. We can also potentially execute one of the innocuous switch statement branches if we choose to. And this basically means that we can defeat pointer authentication. So to fix that, we're enabling branch target identification, which is the other Armv9 control flow integrity feature. Once we've done this, Chrome will be full of these kind of BTIC and BTIJ instructions, as well as Packia SP and Ausia SP. And these mean that we can only call this function in very particular ways, and we can only reach particular points in this function. So it gives an attacker much less control over how to actually exploit this function. So it kind of strengthens Pack as well as being secure in its own right. So since the last BlinkOn, we've hardened FFmpeg's landing pads. So we just added supports to upstream FFmpeg for BTI the last time we talked to you. We've now added support for Pack as well, so it's even more secure than it was before. Like I said, pointer authentication is completely enabled in M102, which is very exciting. We've been monitoring the CR bug carefully, and so far we haven't seen any evidence of major issues. Branch target identification is currently undergoing launch review. We plan to start implementing it in M104 and hopefully finish in M105. So we've also got some brand new devices that are capable of running all of this stuff. So we proactively monitor Chrome's code base and ensure that it has no issues running with Pack and BTI. Pack and BTI is also a system thing, so it's most effective when everything in the Android system supports it. So we're doing a little bit of work also to make sure that every Android phone ships with PAC and BTI, and this is the best way that we know how to ensure control flow integrity is applied everywhere. So these new features do come with a little bit of a few complications. So whenever we do any work on Chrome, we're always trying to strike a balance between performance and security, as well as binary size. So we want the browser to be as secure, but also as fast and small as possible. And at the moment, we've kind of tipped the scales in favor of security. This section is about what we're planning to do to kind of tilt the scales back in the other direction. So with PAC and BTI, at least on the 1+10 Pro, in the production configuration of Chrome, so its official build, we do lose about sort of 5% in terms of performance, and we lose about 5% on binary size as well. And I'm not going to sugarcoat it. It's not great, but fortunately there are some things we can do about it, which takes us on to our performance optimization strategy for Armv9. So the first major component of our strategy is to improve the optimization of critical components for performance. So Salome worked very hard on this, on improving the optimization level in Blink. So essentially the core hot gen component contains all of the HTML parsing, CSS tokenizing, layouts, everything that's essential for performance on this benchmark. It was built with a high level of optimization, but not the highest level of optimization. So we've upgraded the optimization. We've also included some new functions. It's a fairly laborious technique. There's a lot of iteration required, and it doesn't really scale across everything in the code base. But in this particular case, it was very effective, and that should ship in M103. So basically, if we do these core hot optimizations, we can recover most of the performance back from PAC and BTI. So we're now kind of 1% down on where we were when we started. And so that's significant progress. And essentially, we've kind of mitigated much of the performance impact of PAC and BTI. There are some other things we can do. One option that I've been looking at since recently is f-strict aliasing. It's the kind of typical thing that we look at and could potentially deploy. It's slightly faster than PAC and BTI baseline, at least on the devices that we've tested on so far. Pinpoint disagrees about whether it's actually faster or not. The evidence base is not quite there yet, but that could be something that we're looking into in the near future. Another interesting experiment we did was around removing software stack protection. So software stack protection is kind of what we have to rely on if we don't have PAC and BTI. But if we have PAC, then the question comes: do we really need the software stack protection? And if we remove it, then we recover a bit more performance. So we're still not quite as fast as we are on the baseline, but we're getting closer. This is something you could only do as a streamed Armv9 build, though. But we know there's even more effective things we can do, which is why another major part of our strategy is improving profile-guided optimization and automatic feedback-directed optimization. So we've done some major work in the last few years to improve AFDO on Arm, adding support for core sites and making sure that all of the tooling works correctly. AFDO is a very interesting approach to optimization. It enables you to use reports that you gather in the field. At the moment, Android uses kind of in-the-field data from Chrome OS devices. The problem with the AFDO is it does lag a little bit behind the latest code base. It takes a little while for Chrome Stable to be widely deployed and you start to get the AFDO metrics in. So we've also been looking into PGO, and PGO is a very interesting, produces a very interesting chart you'll see in a sec. Essentially, both techniques kind of do the same thing. They both give the compiler much more information on what the compiler has to optimize. So it can help with things like block layout, so making sure that code is kind of ordered optimally within a given function. It can majorly help with inlining as well, so it can decide to take a function from one part of the code base and kind of stick it somewhere else, independently of any headers. And it's also very helpful for things like loop unrolling as well, because it helps you decide essentially how long your average loop is, and is it worth generating some optimized version of that loop in order to make that faster. And basically, when we borrowed PGI profiles from another platform, we recovered a substantial amount of performance. In fact, even more than the baseline AFDO build. So we saw roughly a 23% uplift over the baseline build, and roughly a 30% uplift over the Pack and BCI build. The major casualty, of course, is binary size. We get a significant uplift in performance, but we do get a little bit more binary size relative to just Pack and BCI. Overall, we calculate that for every 1% binary size you kind of put into this, you get about 3% performance benefit. So that's our current best known intervention to improve the performance on Arm. And similarly, the other thing that Salome worked on was actually using this tool HeapTrack to investigate the allocation pattern in Chrome. So the tool reveals some very interesting things about the speedometer workload in particular. So there's roughly 6 million allocations throughout this particular benchmark, and roughly 15% of them don't ever make it out of the original stack frame. So essentially, we run the function, it does some work, the memory kind of is requested from the allocator as a temporary buffer or something like that. The function does its thing, and then the memory is freed and it goes away. In a world with MTE, allocation freeing becomes much more expensive because we have to retag areas of memory that are freed in order to be secure. So anything we can move to the stack is quite a big performance win, and this tool helps us identify areas that might benefit from that. The other interesting tidbit was that roughly 16% of the allocation requests were for things that were less than 8 bytes in size, which again was quite a surprising result, and I'm sure there's something that we can do about that. So essentially, that's the summary. Like with all optimization strategies, doing less often is good. So if we can use PGO and AFDO to reduce the number of functions, increase the inlining, then that's a win for performance. Similarly, if we can reduce BCI landing pads as much as possible, that's good for security. And similarly, reducing temporary memory allocations is one of our key optimization pillars for MTE as well. So I expect that this is what we'll be doing a lot of over the next year. So with that, I'd like to thank you for listening, and let's go to questions. Jonathan, any interesting questions from the chat?
So we have the first one from Andrew Bruce, CFI. CFI is control flow integrity, yes. Other than that, we haven't got any questions at the moment. How about the Q&A pane? No.
Cool, excellent. Well, that's if you do have questions, be sure to. I'm sure that we'll hang out in Kumo space, and we're also reachable via the front page in this presentation. So it's just our.name@arm.com. So that's do get in touch if you have any questions about what we're up to. Yeah, come on. Yeah, I'll just switch over to the chat. Cool, awesome. Well, thanks, guys. We'll hang around in Kuma Space later for if you have any more questions to approach. So, cool. Thanks. Bye.